Yeah, very good evening to all of you. So I welcome you all in the third lecture of this series entitled Digital Elevation Model and its Derivatives for Hydrological Modeling. So here in this lecture, I will be covering definition and synonyms of the digital elevation model, then generation processes of DEM, DM online sources, and finally its applications. So let us start with the introduction to DEM. DEM is basically acronym for the digital elevation model, which is nothing but the digital representation of the elevations distributed over the space, or we can say the continuous variation of relief over space, where relief refers to the height of Earth's surface with respect to the datum considered. Just remember one thing: without any datum, the spatial distribution of elevation doesn't mean anything. So for any creation of the DM or for any spatial distribution of the data, a datum is required. With then digital elevation model representation of the is the representation of the altitude or elevation. This is the altitude of the terrain surface. So you can see a matrix of 6 by 6 is shown in the slide, where the numbers are written in each grid. So these numbers are representing the elevation. So 787 centi, this is the elevation of that grid with respect to some datum. So if this surface is combined with the terrain information such as land use, soil type, rock type, or hydrological condition, then it will be called as the digital terrain model. So here we came to the difference between the DEM and DTM. DEM is nothing but the digital representation of the elevation over the surface, over the space, and when this information of DEM is combined with some other terrain information, then it will be called as the digital terrain model, that is DTM. Now one another term comes into the picture occasionally, which is the DSM. DSM is means the digital surface model. This is the very first reflective surface model that contains elevations of natural terrain features in addition to vegetation and cultural features such as building and roads. So any remote sensing sensor captures first the surface spectra. So first thing we can get is the digital surface model, and DTM is the bare earth model that contains elevation of natural terrain features such as barren ridge tops and river valleys, elevation of vegetation and cultural features such as building, roads, and other things. Other these man-made features are digitally removed. So in the picture you can see one red line is there and one slight blue line is there. So blue line is representation of the digital terrain model, and red line is showing the digital surface model, that is the surface reflectance of the top of the buildings or other cultural or vegetation features. So we can say that digital surface model is a superset of digital elevation model and digital terrain model. And remote sensing generally captures the surface height. So the top of tree canopy or building is written, not the bare ground elevation. So first thing we get is the DSM, digital surface model. And if this data is corrected to remove elements which extrude above the terrain height, you will be left with the DTM. Now here are in this slide two pictures are shown. The first picture is showing the digital surface model where the canopy height and building height and etc. man-made features are shown. And in the second picture, these features are removed and we are left with the bare earth model, which is terrain model. And DTM and DEM, like other vector data, it is not having any scale, but it is having a spatial resolution. Spatial resolution of digital elevation model depends on the spacing between different grids or the different control lines. So here we can say see that the in first picture it is the high resolution DTM where the spacing between the contour lines or grid points are very less in comparison to the second picture, which is a low resolution DTM. Here we have seen our river network, river channel in low resolution DM and high resolution DM. The first picture, it is showing the low resolution where the picture is a slight blurry because the grid size is more, and in second picture grid size is less, so it will be a high resolution DEM. So what is the objective to define these things? Let us see this example. Here two pictures are shown. First is the high resolution 30 meter cell size, and second is the lower resolution 100 meter cell size. So we can see in the circle our river reach is visible in 30 meter special resolution DEM, and however it is not visible in the 100 meter special resolution data. So it depends on the objective for what you are creating or you are processing the digital elevation model. So it depends on the application which special resolution data you have to use. Now comes to the data structure. DEM can be categorized into two main type of data structure. First is the grid structure, which is a matrix kind of system. So square matrix or rectangular matrix kind of system where the different grids are there, and each grid is having some digital number, which is this is the representation of the elevation. And the another data structure type is the tin structure, triangulated irregular network, where XYZ elevation at XYZ coordinates at surface specific points of terrain are recorded. And in grid structure, the elevation for each node of grid is recorded. So the difference is there only. All undulations of terrain can't be covered in a cell size of grid in the grid structure type. However, in tin, it represents more true surface. So tin is always better than the grid structure, but it is very difficult to create the tin type of data structure. Now, various methods for collecting the DEM data can be grouped as spot heights, stereo images, and remote sensing techniques. So spot heights are generally the surveying type of techniques. I'll explain in later slides. So here we can categorize the generation of DEM in four different types. Interpolation techniques, where the points and line data are to be used. Then the photogrammetric techniques, and then interferometry, where the radar data has to be used. Then altimeter and lidar data has to be used. And topographic parameter can be extracted like slope, aspect, 3D view, hill shading, curvature, flow direction, accumulation, channel network, time area curve, river cross section area, and volume. So we will see these parameters in detail in concurrent slides. Now we'll talk about the generation of DEM. There are four different methods I told you. So first method is the interpolation technique, where spot heights are to be measured. So this includes all the methods in which XYZ coordinate of a point can be found. For example, digital levels, theodolite, total station. So these are all the survey instrument where the in that survey the elevation of a particular point has to be measured, and then finally these different points and data has to be interpolated, and finally the topographic map prepared by this method is also and it is also a good and cheaper source for the DEM generations. So for example, this is the texture measurement has to be taken place, and some random points elevation has to be surveyed, and then finally interpolation has to be done and converted into an elevation surface. So with this method it is costly and time consuming to cover the bigger area. So we can't go for the survey for a bigger hectares of the areas. So that's why the remote sensing technique has to be used to cover the larger areas in less time, and it will be cost effective also. So now photogrammetric techniques. So first I'll talk about the DEM generation from stereo images. So stereo images are nothing but the two images captured from the different location for the same area. So that means when two images are captured from different location for the same area, then in the overlapped area can be seen in 3D, and XYZ for any point can be measure. So if you came across the 3D picture, 3D pictures, how 3D pictures can be created, the directors or the cameramen, there will be two cameras in different position, and they capture the same shot with two different angles and just merge them to create the 3D. So that's how we can see the 3D films. And a live example is that a man with single eye cannot see the 3D. We can see the 3D of any particular thing because we have two eyes. So there is a physics behind that, that is called as the parallax. So based on the parallax system, we can see the 3D. The same principle is applied to the stereo pairs also, stereo images also, where two images are captured from different location for the same area. And stereo images can be aerial, satellite or radar images. Images taken from aerial platform have very good resolution but can cover the less area because the distance from the Earth surface to the aerial platform is less compared to the satellite or radar images. Satellite stereo image can be acquired either along path or across path of the satellite orbit. And then now I'll tell you what is along path and across path. Across path is the just in the perpendicular of the flight direction, and along path is the along with the flight direction. So if a flight is moving or satellite platform is moving and it can capture the image along the flight direction, then it will be a long path. However, otherwise, if it is moving the camera perpendicular to the flight direction, then it will be a across path image capturing. So across path stereo images are obtained after revisit period, and hence environmental conditions may not be same. If we want to capture the image for the same area where across path technology is not available, so then the image will be captured in the next orbit, but after some days. So environmental conditions may create some noise in that. And then very high resolution satellite generally capture in pan band and multispectral band of visible region. So this is the pictorial diagram of the stereo images parallax system. So first orbital pass is there, second orbital pass is there, and they are capturing the same portion of the Earth with from the two different angles. Then parallax shift between corresponding left hand and right hand image height object will be used to derive the height. So there is a simple mathematical formulations for to calculate the relief measurements from different angles. And these are the sources of stereo pairs. If you want to generate 3D or 3D map or digital elevation model on your own, so you can use the stereo images provided by IIRS, IIRS, QuickWorld, Spot5, Cartoset, ALOS. There are many sources which can provide you the stereo images in different resolutions. Now comes to the third technique, which is the radar interferometry. The principle is more or less same. In interferometry also two images are taken from different vantage points of the same area, and that slight difference in the two images allows us to determine the height of the surface. So here the signal is transmitted from platform. There are two sensors, excuse me, two sensors installed. One is the this transmitter and receiving sensors, so are distance meter apart. So a transmitted wave is shown in the green color and a received wave is shown in the red color. So receiving sensors are two receiving sensors are there. A slight difference is there between two sensors, that is called the baseline. And the technique to generate 3D images from the Earth's surface. A transmit antenna illuminates the terrain with a radar beam which is scattered by the surface, and two receiving antennas with a fixed separation between them, that is called the baseline, record the backscattered radar echo from slightly different positions. So this I have already explained. So there is also a mathematical formulations behind this, and the height of the terrain at any point of the earth can be estimated using the above formulations. Now the fourth technique is the altimeter or lidar based satellite remote sensing. So altimeter satellite generally determines the distance from satellite to the earth's surface by measuring the time taken by the radar pulse to travel from the satellite to surface and back to the satellite. So time taken by the pulse. We have already known that speed is equal to distance upon time. So speed of the wave, so speed of the radar wave already we know. If we know the time to get back the signal, so speed into time will be equal to distance. So that's how we can measure the distance from the satellite to the earth surface. So different points at earth surface shows the different elevations. So that's how we can calculate the elevation of a particular point over the earth's surface. And the surface height is the satellite's distance at the given instant from the reference surface. So corrected height will be equal to altitude minus corrected range. So there is some datum has to be used, so then correction has to be applied. The lidar is the technique, the full form of lidar is the light detection and ranging. It is also used as similar to the altimeters to measure the height of given object or terrain features by using laser in place of the microwave radiation. In altimetry, the radar echoes or microwave radiation has to be used. However, in lidar, the laser light has to be used. And the principle is same. The time travel time between the satellite to Earth's surface and back from the Earth's surface to satellite is to be counted, and then multiply with the speed of the light, and it will give you the distance. And then finally, correction of the height has to be taken place. So these are the examples of multiple written from a tree. Lidar has better, much more advantage than any remote sensing technique, because it can penetrate through the different layers. Like from the tree, you can see the first canopy layer, it is showing the written, second canopy layer, third written, fourth written, and last written from the bare earth. So it is showing different amplitude and different. So the tree canopy or the branch height also can be measured. This is a picture of the lidar data, and the lidar data is will be of very high resolution because of the less height from the Earth's surface. The platform is much closer to the Earth's surface. Now comes to the data, DEM data sources. So there are various type of different sources from where DEM can be downloaded. So let's say, for example, Cartosat will gives you the special resolution of 30 meter DEM. SRTM gives 30 meter and 90 meter. Aster gives 30 meter. NED 3 meter, 10 meter, 30 meter, and 60 meter, but it is only for the United States. GMTED, it is global 225 meter, 450 meter, 1 kilometer. These are all the free sources from where you can download the DEM. And JAXA, Spot, GTOPO 30, NOAA, Globe, TandemX based on the radar, this interferometry. That's why the resolution is very high, 5 meter, and Open Series elevation map from the Survey of India. So these are the main sources from where you can download the DEM. Several other sources are also there. There are a long list for the sources, and it depends on the objective for which objective you are using the DEM and what resolution you want, what will be the accuracy level. So there are several criteria you have to finalize before going for a particular source. Now comes to the terrain parameters, that means the DEM derivatives and watershed delineation. So several type of terrain variables which can be extracted from the digital elevation model, like height, slope, aspect, upslope area, flow length, upslope length, profile curvature, plan curvature, and visibility. And in this table, importance is also given, like this aspect will be useful to assess the insolation, temperature, vegetation, soil characteristics, moisture, visibility. Slope will be useful to analyze the water flow, flooding, erosion, travel cost, construction suitability, geology, insulation, soil depth. So these all are parameters are closely attached to each other. So we'll see these parameters one by one. And let me tell you first, before discussing the terrain parameters, the errors in DMs. So there are several errors in DMs where you can download the DM freely available from different sources. So there are several type of errors are there. So most common variety of the errors are sinks and spares. So sinks occur where a very low elevation relative to surrounding cells is entered, and spires occur when a very high elevation relative to surrounding cells is entered. So both appear as tightly pegged contours. So better to remove these type of errors before proceeding ahead. So how to remove these errors? So sync can be, for example, sync is showing the very low resolution related to the surrounding cells. So what we can do, the surrounding cells, suppose 9 by 3 by 3 matrix is there, and center pixel is showing the low resolution, the lower elevation value. So what we can do, the lowest value from the surrounding pixels is to be filled at the place of the sink, and similarly in spares the highest value in the surrounding pixel has to be fixed in the middle pixel to remove the spares and sinks. So first error removal has to be takes place before derivation of any terrain parameters. Now comes to the very first raw parameter of the which can be derived from the DM is the slope. Slope controls the flow distribution and movement, land utilization, and watershed behavior. And in water resources aspect, we can say that the slope is playing very dominated role, because the if slope is more, flow velocity is more, hence the flood water drains quickly, results in higher peak discharge, reduces the infiltration, increases the soil transportation. So slope is very important, and it can be calculated locally using a neighborhood function based on a moving 3 by 3 window. So we can see a matrix here. So center pixel is designated as 0, and 111 is in 4 pixels, surrounding 4 pixels, 111 is written. It is the distance from the pixel to pixel, and however the diagonal pixel, it is representing as 1.41. So under root 1 square plus 1 square, that means under root 2, 1.414. So diagonally the grid spacing is 1.414 meter. However, longitudinal or lateral, the grid size is only 1 meter. So slope has to be calculated as the elevation of one grid point minus elevation of a second grid point divided by the distance between the grid point, horizontal, vertical, or diagonal. So steepest slope are to be used. Now this already I explained. Slope is rise or run. So rise divided by run. That means the rise means elevation difference. Run is the horizontal this planimetric distance, grid size. Like for example, these in first matrix the elevations are shown. In second matrix the slope calculation has to be is shown. The middle pixel is showing 0, and the farthest left pixel 340 minus 332, it is 8 divided by 42.47, because the here the grid size is 30 meters, so 30 into 1.41, it is 42.47. So that's how the slope is calculated, and this is the classified slope map. Now comes to the aspect, the second important parameter. It is the compass direction that a slope faces. So for example, a slope on the eastern edge of the mountain toward the Great Plains is described as having an easterly aspect. Similarly, a slope which falls down to a deep valley on its western side and a shallower one on its eastern side has a westerly aspect. So generally, the aspect is expressed in the azimuth angle. So that means the angle from the north direction. So easterly aspect, westerly aspect, southerly aspect. So it is generally expressed in the azimuth angle, and angle calculated from the azimuth north. And aspect can have a strong influence on temperature. The aspect of a slope can make very significant influence on its local climate, or we can say the microclimate. For example, because the sun rays are in west at the hottest time of the day in the afternoon, in most cases a west facing slope will be warmer than a sheltered east facing slope. And this is the aspect map of the watershed. And these are all the derivatives created from the raw digital elevation model only. Then the flow direction, there are two type of algorithm has to be used to calculate the direction of flow. First is the D8 algorithm. So that means the 8 directions are shown: 1, 2, 4, 8, 16, 32, 64 and 128. So 1 represents the eastern direction. So then slope already we have. So D8 algorithm, or we can say that the direction of steepest descent, the principle of direction of steepest descent has to be applied to in the D8 algorithm to calculate the flow direction. So slope has to be calculated and steepest one has to be taken as the flow direction. There is another algorithm which is called as the D infinity algorithm. Like in first D8 algorithm, only 8 directional slope has to be calculated. Here in infinite, that means the infinite direction slope has to be calculated. So, or we can say that flow direction angle is determined as the direction of steepest downward slope on the 8 triangular facet formed in a 3x3 grid cell window centered on a grid cell of interest. The resulting flow in a grid is then usually interpreted as being proportion between the two neighboring cells. So that's how the infinite direction can be created. And the steepest direction downslope will be the direction of flow. So generally in our hydrological modeling software and other GIS software, D8 algorithm is only applied. This is the flow direction map of a watershed shown in different 8 directions of the flow. And with the help of flow direction, we can calculate the flow accumulation. So in the first top picture, it is showing the flow direction in terms of the number 1, 2, 4, 8, 16, 32, 64 and 128. It is showing the direction. So assign the value to indicate the direction of flow. Then for each cell, determine the number of cells upstream from the that means the contributing area of a particular grid cell has to be identified, and then adding the number. So cumulative number, that means the at particular grid point how many grids are contributing to that grid. So that is called the flow accumulation. Like in right hand side, very right picture, flow accumulation grid has to be shown. So the boundary pixel is 0, 0 or 1, 1. And the middle picture, grids are showing as 3, 2, 2. That means the where the 3 is written, 3 pixels are contributing for that pixel. 2 means 2 pixels are contributing that pixel. So finally, in cumulative way, at the down 24 is written. That means at that grid point, cumulatively 24 pixels are contributing. So that's how the flow accumulation map has to be prepared. And after this setting a threshold for the minimum value of flow accumulation, which defines a stream, we can arrive for the stream network. Suppose the stream threshold of 5 has to be applied, then 11, 15, 24, this is only the stream, the part of the stream network. So this is the flow accumulation map, where the different classes of flow accumulation. That means the classes, it is written like the first gray color is showing the 0 to 1000. That means the 0 to 1000 number of pixels are contributing to that point. And after the thresholding, the stream network extracted from the flow accumulation map. and the red line is showing it is the main stream after a greater threshold. Then stream ordering can be done. So there are two different techniques to order the stream, strealer and stream. So generally we are using the strealer, where the two first order streams joins together to create a second order, and second order and first order streams joins together to continue the second order streams. Only the when two similar order streams joins, then only the order will be increased by one. Otherwise, the order will remain same. And flow length also can be measured with the help of the flow accumulation and stream network. So this is the flow length map of a watershed, where from the outlet point how much distance is there for each pixel. So this is the flow length map. This is the flow direction map. Already we have covered it, flow accumulation. This is the drainage map. And finally, after the stream network identification, we can create the sub-catchment map, or we can say the sub-watershed map. Now comes to the another parameter, which is the hill shading, where the shadow filter has to be applied. It is the standard linear filter which works in a 3x3 environment, and the value of matrix are as shown. And the main purpose of hill shading filter is that it eliminates the direction. The illumination direction can be varied by mirroring the values of the matrix. So that means the sun's direction or the illumination direction, we can move from a particular direction, and where the watershed or where the this elevation shadow goes. So that is applies. That means it applies the artificial illumination to the DM. As a result, higher parts in DM become more pronounced because they obtain a shadow. In different software like ArcGIS, IIRS, we can have the option for the illumination sources, and it can be changed also. And for example, this is the first picture. It is showing the digital elevation model, and in second part, it is showing the shadow image. So illumination direction, if it is kept as the northwestern, so how the shadow moves, and if we can move the illumination direction, the shadow also moves. So it is basically for the this identification of the critical area for installation of some field instruments or some special type of varieties of crops has to be shown. So this is for that purpose only. So this is the hill shading map. Then the curvature of terrain, there are three types of curvatures: convex, concave, and flat. So the Laplace filter has to be applied, which is a standard linear filter which works in a 2x3 window, and the value of matrix are 1 except the central pixel, which is -8. And convex convex sorry, convex means the negative value. That is that means the it is where the curvature is convex, the flow accumulation will not be takes place. Where the concave type of curvature is there, so flow accumulation takes place on that area. However, flat areas or uniform slopes obtain zero values. So this is the curvature map. We can see the concave area where the green patches are there. So it is showing the river valley path, and the blue portion is showing the higher elevations where the convex curvature is there. So this is also to identify the stream network and other applications. And whatever derivatives I explained, this is obtained from only raw DM and GIS environment. Some other DM derivatives are also there, which is mainly for the purpose of the applications in water resources. So first is the compound topographic index, also called as the CTI. So it represents the tendency to accumulate water of a pixel with a low slope angle is greater than one of a very steep pixel. So it shows the tendency to accumulate water. Commonly, it is very commonly used parameter to describe this tendency. CTI is equal to logarithmic of AF, that means the flow accumulation or the specific catchment area draining through the point, that is the flow accumulation, divided by tangent of beta. And it is also called sometimes as topographic moisture index or wetness index. And for the same contributing area, CTI is higher for the pixels with lower slope. Why? Because the tangent of beta is low, so CTI will be higher, where the flow accumulation remains constant. This means CTI primarily reflects the accumulation process. So where low slope area is there, flow accumulation tendency is more. And the other parameters are stream power index and sediment transport index. Stream power index is used to reflect the erosive power of the terrain, and that is the multiplication of flow accumulation into tangent of beta. However, sediment transport index, it is to reflect the erosive power of overland flow. It is also a function of flow accumulation and signage of beta slope. Now some morphometric parameters also can be derived, like drainage density. It is the ratio of total length of all streams of the catchment divided by its area. Stream density, which is the number of streams of given order per square kilometer computed by dividing the total number of streams with area. In drainage density, it is the total length of stream divided by area, and in stream density, it is the number of streams, total number of streams divided by area. And the shape factor, it is the ratio of square of watershed length to the watershed area. Channel slope, centroid of the basin. Form factor is the ratio of watershed area to the square of its length. And shape factor is the reciprocal of the form factor. Then compactness coefficient, which is the ratio of the perimeter of the basin to the circumference of a circle with equal area. So that means consider a circle of the area as same as the watershed, and the ratio of perimeter of the watershed divided by circumference of that circle, which gives you the compactness coefficient. Then elongation ratio, which is the ratio of diameter of the circle of the same area to the maximum length of the basin. So here also consider a circle of the same area as the area of the watershed, and the ratio of diameter of the circle to the maximum length of the basin gives you the elongation ratio. How much elongated is my watershed is. Then circulatory ratio, it is the ratio of the basin area to the area of circle having the same perimeter as the basin. And the very classic use of the classic derivative of the DM is the hypsometric curve. Hypsometric curve is an cumulative distribution function of elevations in the catchment. And it essentially a graph shows the proportion of land area that exists at different elevations by plotting relative area against relative height. So in that figure, it is showing the hypsometric curve of our globe. So you can see the elevation meters below the earth surface, that means the below sea level and the above sea level. So how much proportion of the land area or how much proportion of the ocean area represents which class of the elevation. So we can see the highest proportion of the land represents the area from 0 to 1000 meters. And below the sea level, the highest proportion is 23.3. That means the 4000 to 5000 meters. So the ocean is much more deeper than the surface over the earth. So that is the how we can interpret the hypsometric curve. So these are all the derivatives. Now I'll talk about some very brief applications of DEM, digital elevation model. Orthophoto production and topographic mapping. DM is needed for ortho-rectification of an image. The process of removing the effects of sensor tilt and relief to obtain a photographic map with uniform scale. So ortho rectification if you might have heard this word or ortho rectification, that means the rectification of any image from the geometric point of view. So DM is very much required to ortho rectify any kind of image or other thematic image like land use or soil map and other thematic maps. So which can be ortho rectified with the help of digital elevation model. And then comparison of drainage maps. So drainage maps or topographic maps, like topographic maps which has to be supplied by Survey of India or other old topographic maps, so in which the drainage maps are mapped. So DEM can be used to recheck these drainage lines by using the digitization techniques and other GIS techniques, and overlay the old map to the newer map and just change the maps accordingly. Then hydrological and flood modeling. DEM is the very primary, or you can say the building block of any type of hydrological model. So without DEM, we can't set a hydrological or flood model. So this is the very basic input parameter. Visibility analysis also can be done. This is the 3D pictorial view. If you see, you have came across the Google Earth, so you can rotate the viewer angle in the Google Earth also. So that's how we can do the visibility analysis using a digital elevation model. Without the 3D picture of the land area, we can't use this functionality. Then surface draping, it is a very beautiful application. Suppose if we have the rainfall map and the digital elevation model we have, and we want to see the rainfall pattern according to the different elevation areas or different slope area. So we can just drap or overlay the rainfall map over the DEM. So that drapped image will be the combination of rainfall data over the elevation profile. Similarly, perspective view of the DEM also can be generated, where the FCC, this false color composite image, can be draped over the digital elevation model, and the 3D representation of the different natural or other cultural features also can be created. So that's all from my side. That's the time of discussion. So if anybody is having any query or want to discuss something, so welcome.